In differential calculus, an inflection point, point of inflection, flex, or inflection is a point on a curve at which the curve changes from being concave to convex, or vice versa. A point where the curvature vanishes but does not change sign is sometimes called the point of undulation or undulation point. In algebraic geometry, an inflection point is defined slightly more generally, as a point where the tangent meets the curve to order at least 3, and an undulation point or hyperflex is defined as a point where the tangent meets the curve to order at least 4. Definition: a differentiable function has an inflection point if and only if its first derivative, f, has an isolated extreme at x. That is, in some neighborhood, x is the one and only point at which f has a minimum or maximum. If all extrema of f are isolated, then an inflection point is a point on the graph of f at which the tangent crosses the curve. A rising point of inflection is an inflection point where the derivative has a local minimum, and a falling point of inflection is a point where the derivative has a local maximum. For an algebraic curve, a non-singular point is an inflection point if and only if the multiplicity of the intersection of the tangent line and the curve is odd and greater than 2. For a curve given by parametric equations, a point is an inflection point if its signed curvature changes from plus to minus or from minus to plus, i.e., changes sign. For a twice differentiable function, an inflection point is a point on the graph at which the second derivative has an isolated zero and changes of sign. A necessary but not sufficient condition: if x is an inflection point for f, then the second derivative, f, is equal to 0 if it exists. But this condition does not provide a sufficient definition of a point of inflection. One also needs the lowest order non-zero derivative to be of odd order. If the lowest order non-zero derivative is of even order, the point is not a point of inflection, but an undulation point. However, in algebraic geometry, both inflection points and undulation points are usually called inflection points. An example of such an undulation point is x equals 0 for the function f given by f equals x4. This definition assumes that f has some higher-order non-zero derivative at x, which is not necessarily the case, but if it has one, it follows from the definition that the sign of f is the same on either side of x in a neighborhood of x. If this is positive, the point is a rising point of inflection. If it is negative, the point is a falling point of inflection. Inflection points. Sufficient conditions. 1. A sufficient existence condition for a point of inflection is: if f is k times continuously differentiable in a certain neighborhood of a point x with k odd in k3, while f equals 0 for n equals 2, k1 and f0, then f has a point of inflection at x0. 2. Another sufficient existence condition requires f and f to have opposite signs in the neighborhood of x. Categorization of points of inflection. Points of inflection can also be categorized according to whether f is 0 or not 0. If f is 0, the point is a stationary point of inflection. If f is not 0, the point is a non-stationary point of inflection. An example of a saddle point is the point on the graph y equals x3. The tangent is the x-axis, which cuts the graph at this point. A non-stationary point of inflection can be visualized if the graph y equals x3 is rotated slightly about the origin. The tangent at the origin still cuts the graph in two, but its gradient is non-zero. Functions with discontinuities. Some functions change concavity without having points of inflection. Instead, they can change concavity around vertical asymptotes or discontinuities. Take, for example, the function 2 by 2. It is concave when x greater than 1 and convex when x less than 1. However, it has no points of inflection because 1 and -1 are not in the domain of the function.